We're doing the propagation of error lab today, and I try to do this both semesters in other words, in my PHY 241 as well as in my PHY 242, because some students take 241 other places and then get 242 here, and vice versa. So I want to make sure everybody that goes through physics at least calculus-based physics, and I try to do it with a 201 as well, but we have a streamlined version that doesn't include the calculus. But as well as the people in 201 and 202, I also try to make sure everybody that's gone through our physics at TCC understand how error propagation works. The gold standard is not sig figs. No real serious scientist uses sig figs except maybe as a first order approximation. The way you actually trace out how error goes is a process called propagation of error, and there's a ton of books on it. Taylor has probably the most famous one. It has a cool picture of a train that sort of launches out of this window in a building and then falls down into the streets. You've probably seen it. It's a pretty famous photo. But Taylor's book has that on the cover, and that's probably the most famous book on propagation of error for scientists. There's other ones as well. They're all really good. I don't think I have any of them here. That's why I just called it Taylor as opposed to giving you the title of it. Uh, I think it's Measurement and Uncertainty, something like that, one of those type titles. But we're going to discuss that for this lab, and your job is to complete a document and turn that back in. The good news is the document requires some pretty rough stuff, which is sort of the bad news, but the good news is I teach you how to do it right here. We're going to, for instance, have to use what's called a partial derivative, which is something that you normally don't learn until the third semester of calculus, and this course only requires Calc 1. So it's, again, one of those instances where in physics, you're going, art and engineering for that matter, art and chemistry for that matter. Basically, in your sciences, you will often learn how to do mathematics before you ever get to the equivalent mathematics course at which that would be taught. I usually tell my students about I got a chance to take differential geometry, which is one of the fundamental courses that are basically a fundamental branch of mathematics that general relativity depends on. So I got to take a graduate level course, and literally on the last day of the whole one semester course, we were just getting to covariant derivatives. And the first day of general relativity, they taught us how to do covariant derivatives. So you can imagine that's kind of a bummer. Like literally, that's I got some other stuff out of the course, of course. I mean, any math course can teach you a lot of good stuff. It's just is very irrelevant to general relativity, other than just a broader understanding. So that's the way things work in the sciences and engineering. Is a lot of time you're just not going to be able to get to the math in your math classes, and even when you do, sometimes they do it entirely differently. So, for instance, differential geometry was entirely different in the mathematics class than it was in my general relativity course, mainly because they just do a lot of things with parameterizations as opposed to just normal functions and stuff like that. So they just look at it a little differently. Everything's completely equivalent, and to be honest with you, there wasn't very many books that I was able to find until much later that showed you how to do the stuff the way physicists do. So we just sort of go by word of mouth. One instructor teaches a student, and then that student teaches other students, and then that student ultimately teaches another student that becomes a instructor, and we go on and go on. So, anyways, I'll get off my soapbox on that, and I'm going to go ahead and start off by sharing my screen so you'll see the document that I'm talking about. So let me do share screen. It's this screen, but I'm on the wrong window, so let me get to the right window. So this is the lab we'll be doing. Actually, let me show you first. If you go to our module or our Canvas course. This is where you should start in your Canvas course period for my online classes, whether it be NO2B or O01B, our PHY 241, our PHY 242. If you're looking on Canvas, even face-to-face classes, the first thing you should do is go to Canvas and then go to the modules. Modules and home pretty much look the same, but let me show you the difference. It's really not much. It's more of a difference from an instructor standpoint because I don't have these options over here. So it's really not that much of a difference. But the main thing is the modules is where I want you guys to start off. The reason being is it has these modules where you have helpful documents and links. You have my Zoom office hours slash class invitations. You have interesting science related links and documents. So this is stuff that I refer to from time to time, but it also turns out to be just some interesting stuff from a physics standpoint. This is my personal interest, which occasionally people ask about. I don't put it up there because, I want people to learn all this extra stuff from me. It's just the kind of things that I like reading about, and I think educators should educate in all fields that they have any knowledge in that's appreciable. So, anyways, that's what there. Then we have the chapter practice. As I told you, those are a practice where I don't, they never go to my grade book, but I can tell how much you're taking them. And they're basically just chapter problems that are focused on an individual chapter. So when you get to a point on your practice test that you realize it's only chapter 4 that's giving me a problem, then you should come and take chapter 4 practice a couple times, and that should work it out. You can see it's for each of the chapters that we plan on covering this semester. That's 1 through 10, 11, 14, and 15. And like I said, we often cover relativity, which is chapter 36. Anything outside of these, excluding chapter 36 right now, is going to be extra credit. If I happen to get to chapter 36 in the summer, which I'm almost certain not to, then it will not be extra credit, but chances are everything, it and everything else will be extra credit. Here's where the practice tests are. Here's where the online tests will be. Here's where the face-to-face tests will be. And this is where the proctored final exam will be. Again, proctor just means you're going to have Respondus lockdown browser and Respondus monitor on. Here's something that you guys can't see, but here's my first week. And in the first week, we covered chapter 1. And here's the homeworks for it. And the reason why I'm telling you all this about going through the modules of Canvas is because of this. My students inevitably will find some assignment that's still in Canvas, and I just haven't figured out how to get rid of it because I copy courses from previous semesters into here, so it keeps popping back up. And my student will email me and say, how do I, when do I do this assignment? Or I missed this assignment or something like that. And I look at it and I'm like, it's not even an assignment that I assigned this semester. So if you find anything like that, if it's not in these modules, then you do not have to do it. Okay. If it's not in one of these modules, it's not required for you to do. And some of the things that are in these modules are not required either. That's why I call them extra credit, for instance. So, anyways, that's what that's about. These are all optional videos that go in addition to the ones I'm making in real time for you guys. So if you ever need a booster or some extra experience, these are all videos that you can look at. As I mentioned to you, if they have the LEC in it, that means they're full length and they're lectures. So you'd have to cut and go through them, fast forward till you get to an example, watch the example, then fast forward to another example, that sort of stuff. The other ones that don't say LEC or lecture, they're sometimes actual individual problems like this one is, and this one is, and this one is. So keep that in mind. Now, the relevant part is today's lab. So Tuesday lab, we did introduction to lab, and I gave you these comments so you could read before you turned in your assignment, because once you read this, you'll find out common errors that students make. So hopefully you will find those errors before you turn them in, and then you'll turn them in here. The good news is if you haven't yet, or even if you have turned it in already, but you didn't look at that, you can now go back and look at that. And if you see any mistakes you made, just go ahead and correct them and resubmit, because I only check the last lab that you turned in. So if you turn in 14 copies, I'm going to only look at the last. But that also means I'm only going to look at the last. So if you think another one's better, you better erase the other ones if you can, or let me know exactly which ones are not to be read. Uh, Today's lab is the Thursday lab, of course, and this is the document I'm talking about, Lab Error Propagation Part 1.5. That's the Word document that you normally expect to have. These are the comments, just like I told you on the last lab, and this is where you turn it in. If you'll notice when you click on this, it is a turn-in location, but it also has the document itself up there, and it also has the generic instructions I've told you about turning in your lab report. So this is all stuff that you're supposed to know about. Your job again to turn in a lab report is to take that Word document that we supply, type in all the relevant data in a font other than black. Anything you type into the document needs to be a font other than black so that I can immediately identify what you typed in versus what was already in the manual or the document. You're supposed to, of course, do a sample calculation of each type of calculation that you do in the lab, even if the lab doesn't ask you for it. If you are told to print something, that means you're supposed to take a photo of the screen, the relevant part of the screen at least, and then paste that into the Word document right where they told you to print it or right where you were made to or suggested to make the actual graph or whatever it is you're taking a picture of. Same thing with the questions. If you run into a question, you're supposed to click right up to the right of the question mark, hit return, 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 and then in the middle of that white space, type in the answer to those questions. So every question you see in the lab manual needs to be answered. Every blank, unless I explicitly tell you otherwise, every blank has to be filled in. Uh, every time you write a number, if it has a unit, then you need to include the unit or make some way for me to understand what the unit is, all that kind of stuff. But all that's spelled out here. This is probably the last time I'm going to re-go over this. So I did it on the first lab and I did it on this lab, but I'm probably not going to do it in the future. So we can go back to the modules. As I told you, we're in week one lab module, and we're doing specifically the lab error propagation part 1.5, and that's this document right here. So your job in this document is to read it in its entirety and make some sense of it. You can actually look, I have several lectures of it online on my YouTube channel, so you can do error propagation, do a search for error propagation, or even the word propagation would probably be sufficient, and you'll find lectures of it. But the main thing is that sig figs don't work that well. They're just a good, quick and dirty approximation to how numbers should be treated when you have a number with uncertainty, and then you have another number with some uncertainty, and then you have to combine those numbers by adding, subtracting, multiplying, dividing, or doing some other mathematical operations like take the sign of one number or the sign of the ratio of two numbers or something like that. All of those things lead to yet another number, and as a scientist, you need to know if I put in, numbers that have a certain uncertainty, and then they do some mathematical operation on those numbers, what's the uncertainty of the result? That's really what we're talking about in propagation of error. As you can tell, that's sort of what we're doing with sig figs, because we have rules like when you multiply two numbers, the number with the least number of sig figs is the number that dictates the number of sig figs the answer has. That's the multiplication and division rule. The addition and subtraction rule is the number that you're adding or subtracting that has the lowest precision, i.e. the fewest number of decimal places, dictates the number of decimal places the answer should be rounded to. That's again a propagation of error formula, but it's about sig figs, or in this case, it's about precision, whereas multiplication and division is about sig figs. If you take the sign of a number with uncertainty, then if that number had 4 sig figs, then the sign of it should come out rounded to 4 sig figs. All that being said, I want to remind you that if you're doing some operations like that and then you're going to use that number to make another calculation, then you should carry at least one extra digit for each of those calculations. And the way I tell my students to do that is when you keep that extra digit, just underline it. And even if you turn it in with the underline on it, that would suggest oh, okay, this student has too many digits in there, but he did indicate that this underlying one is not a sig fig. So when I look at the number of sig figs, the answer is right, and I'm not going to take points off. But it also allows you to have the number with the extra digit, so you can use it at any time to do the calculation that you need to do, or to redo it in case you made an error or something like that. So keep that in mind. And every time you're working with sig figs, you do a calculation. You obviously, if you want to tell anybody what that result is, you need to round it to the appropriate number of sig figs. But if you're going to need that number later, you need to keep an extra digit or record it somewhere so that someone can know. And I'm telling you, the way you can do that is always you can carry extra digits and just underline them, and I'll understand what you mean. That is not accepted in the scientific community. It's not something you're going to do on published papers or anything, but it works in my class. Okay. All right, so this tells you about all that. It tells you about, it sort of walks you through a typical experiment, like measuring h, the height of something. You can see here, I said, after several meter stick measurements, you found h equals 56.40 centimeters, 56.38 centimeters, 56.38 centimeters, 56.41 centimeters, 56.40 centimeters, and 56.39 centimeters. Then the most reliable value to use would be the average. So what we're telling you is the best estimate when you make multiple measurements, the best estimate is, and I'm going to give you a caveat to this because this is not 100% true, but the best estimate is generally the average. So if you made five measurements, you sum the five up and then divide by five, and that's your best estimate. And then you round it using sig figs is what we would normally do. But and later we're going to learn that it's not the golden rule. That's not what we're going to be using. Okay, now here's the caveat. And I tell you this just for completeness because we're never, ever, ever going to do this in our labs. But the holy grail of finding the best estimate of a measurement is it's not the average. It's actually the weighted average. So you can't really do that here, but let me explain a little bit what I mean. So, for instance, if you were a big corporation, let's say, and you had labs all over the world, and you were having these individual labs do these same measurements, in other words, every lab is working on the same project, then you have some labs that might be like your number one top experimental physicist or whatever, a bunch of Nobel laureates and stuff like that. That lab is on average likely to have the least amount of error in their lab results, in their labs that they actually do in the experiments that they run. And therefore, you should, in some sense, think that that data is probably a little bit more valuable than any other one. If that really is your greatest scientists, day in and day out, it's much more likely that they will, day in and day out, produce the best results. However, you also have other labs that might be staffed by graduate students, which are pretty good. But then you might have another lab that's staffed by undergraduate students, which can be pretty good too. But they're normally undergraduates be a little less competent than grad students. And then below that might be just practitioners, just technicians, stuff like that. So their error would probably be a little bit less. Now, if you set them all on the same task of, let's say, determining the length of this object, and it could be something really microscopic, so it would make some sense that they just be doing it. But if you really were doing that, then what you could do is take the result from each of your labs, but you want to weigh them properly. And instead of doing just an average of all the lab's reports, you're going to do a weighted average. So if you had a measure of the typical error that your Nobel laureates do, let's say it's 0.001 centimeters is the typical error at your Nobel laureate level. And you say that the grad students have 0.002 centimeters would be their average error, and the undergraduate students would be 0.004 and centimeters again, and maybe the technicians might have 0.005, and then you have lower level labs that are less experienced people, and maybe their maybe their average error is zero point zero 0.01 or something like that. So it's literally a whole magnitude bigger. If that's the case, then you want to weight them. The way you can weight them is you can take the error for that lab, the 0.001, 0.002, 0.003, 0.004, and the zero point zero 0.01, and you can flip them over. Because if you take a really small error, zero point zero zero 0.001, for instance, and flip it over, that takes that point zero, or that takes that 0.001, which is 1/1000th, and flipping it over turns it to 1,000. Now if you take it after flipping it over and square it, then it brings it up to 1,000,000. So you could use that as a weight, the inverse of the square of the lab's average error. uh, as you can see, that would come out to be a multiplier of 1/1,000,000. So that's given the Nobel laureates, for instance, each of their trials will count as 1,000,000 trials. Now, if you do the next level lab, which is made of a bunch of grad students, say, then in that case, they're at the zero point zero zero 0.002 level instead of the zero point zero zero 0.001. So if you take zero point zero zero 0.002, that's 2/1000. So when you flip it over, it's 1,000 divided by 2, which is 500. And then you square it, that's 500 times 500, which is 250,000. So they're getting a multiplier of 250,000 by that weight. And you do that with each of the individual labs. You always take their error and either just flip it over or take the error and flip it over and square it. One of those works. Both of those work, in fact. Now, what you're going to do is take that error flipped over and squared, or that error flipped over and not squared, whichever one you choose to do. You're going to take that error and multiply it by the value from that lab. And you're going to take the error for the next lab and multiply it by the value for that lab and all that stuff. Once you're done with making that multiplication of each of those individual labs, you're going to add all those quantities up. So you're going to take the product of the reciprocal of the square of the uncertainty that your Nobel laureate lab has times their result plus the uncertainty that the grad students had squared, in other words, and flipped over times their result plus so on and so forth. Now, to make it weighted, you now have this weird unit of centimeters squared. So what you then do is take and divide up all those things that you considered the weighting. So the 1 over zero point zero zero 0.001 squared, you put that in the denominator. The 1 over zero point zero zero 0.002 squared, you put that in the denominator being added to the last one, and you add all of those, what we're using as weights, you add all those up. So what you end up having now is the product of the uncertainty and the value plus the product of the uncertainty and the value plus the product of the uncertainty and the value, all of that added up on top divided by the sum of the uncertainties, flipped over and squared. And then that ultimately gives you what we call a weighted average. And it's just much more valuable because it's giving the appropriate weight to the really accomplished scientists and the appropriate weight to the less accomplished scientists. So again, that's the caveat. Technically, a weighted average is better than a regular average, but we're always going to use just a regular average when you have multiple trials of some kind of measurement. Okay. Now, in addition to that, when you go to make multiple trials, the first thing you need to do is inspect your measuring device. So if you're using, for instance, a meter stick or a ruler or something like that, let me show you. I don't want that particular ruler. I think I got one in here that's helpful. Okay, and hopefully this isn't so clear that it makes it impossible to see. So what I'll do is I'll put it in front of this paper. I have no idea what the paper is, but you can see right here the bottom scale. I had it at the bottom, now it's the top scale. So you can see how that measuring device is marked out. And when you're using a measuring device, you want to notice some things. One thing you want to notice is exactly where is the zero on the measuring device. and then exactly where is the 1 unit on the measuring device. And then you want to count the number of spaces between the 0 and the 1, or maybe between the 1 and the 2, whichever is easiest for you is fine. So like right now I'm looking at this device, which is marked as a meter stick would be, and it has, for starters, it has the 0 close to the end, but not at the end. So the 0 is close to the end, but not at the end. That's a good thing, because if the meter stick or ruler had been mauled on the end, you wouldn't really know where the 0 is, and then you'd have to make all your measurements from the 1 centimeter mark or the 10 centimeter mark, and then remember to subtract. So it's a bit of a pain. But the main thing is you now know what this meter stick is and how it's measured. Now, when I look again between the 1 and the 0, are between the 1 and the 2, either one we choose to look at. When I look between them, I see there's actually 10 equal size spaces between the 0 and the 1, or between the 1 and the 2. That means each of those is 1/10 of a centimeter, which we also call a millimeter. So that tells you is that the markings on this device are up to the first decimal place in centimeters. So it's a done deal when you make a measurement on this device. If you write it out to 1 decimal place, because that is all clearly marked here. You should definitely never ever have less than 1 decimal place on this, unless you're just trying to rapidly do things in order of magnitude calculations. So not only that, if you actually go to measure something and the you've got one end on the 0 and the other end that lands somewhere between the 5.5 and the 5.6, then since it's certainly past the 5.5, you're going to call it 5.5 something. But what you can tell is, unless you have a really hard time making the measurement, because you're like trying to measure, let's say, a shape like, let's say you have this rigid body and you have no way of getting over to measure this little part right here. So you end up having to do a measurement like this, where you're sort of eyeballing where the 0 lines up with this, and you're trying to eyeball where it lines up with this, and you can't literally get the meter stick up here against it like you want to. That is the type of problem that would introduce more error. And by doing that, you probably have to say, okay, I'm not going to be able to get more than 1 decimal place on this one. Or maybe even I might be able to say, or I might have to say, I can't get better than a whole number on this one if it's really that bad. So if you had extenuating circumstances that make it more difficult for you to actually make the measurement, then the uncertainty in the measurement has to be dictated by those difficulties, not just the measuring device. But otherwise, if you don't have those difficulties, then a measuring device like this, which is in centimeters and has 10 gradations marked out between the first and the 0 and the second centimeter, or between 0 and the first centimeter, then you should be able to get 2 decimal places. And when you have 2 decimal places as your last digit, or as your sig figs go, in other words, when you make a measurement that is measured all the way out to 2 decimal places in centimeters, then by default, the instrumental uncertainty there cannot be any smaller than 1 in that last decimal place. So the uncertainty of such a measurement would be 0.01 minimum. It could be bigger than that, but it's minimum going to be that. Now, if you notice something like, oh, wow, it turns out that this rectangular thing that I'm trying to measure, let's say maybe this rectangular thing that I'm trying to measure, if you find out that this edge is not really smooth, or this angle is not really exactly 90, then there might be some problems with your measurements as well. And that also might make it more difficult for you to say that the total number of decimal places this measuring device gives is 2. So those are some things that you should consider. That being said, once you decide on your measurement, how you're measuring it, what kind of difficulties you're going to run into, what kind of weirdness of the shapes you're measuring, then you have to decide, what is my instrumental uncertainty, because that's supposed to be the the best uncertainty that device can give under those circumstances. So you write it down somewhere. You say, okay, I think in this case the uncertainty is plus or minus 0.02 centimeters, or maybe you've got some extenuating circumstances that make you have to reach the conclusion that the uncertainty is zero point zero 0.04 centimeters. So you'd have to measure the device, measure the object, and then record it like 2.54 centimeters plus or minus 0.04 centimeters. Okay. But you have to acknowledge what that instrumental uncertainty is. That's the uncertainty in the instrument. If you're using something that's not like measuring a meter stick, like you're reading a digital scale or a digital readout or something, then what you do, unless you have the owner's manual, is you always assume an uncertainty of 1 in the last decimal place that the measuring device gives you. So you're always going to assume it's at least 1 in that last decimal place that the measuring device gives you. If you have the manual, you'll look in it and it might actually tell you very specifically what the uncertainty is, and you would record that as the instrumental uncertainty. Again, if you still had problems in making the measurement that you suspect make that measurement less than valid, then you might want to adjust the instrumental uncertainty to a little higher. Again, that's a decision you have to make. But once you've worked out all that, you've got your instrumental uncertainty, then your job is to just measure the quantity over and over and over again. If you're measuring something like this, you might measure it here, and then 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 here. So that could give you like 5 or 6 different measurements. Again, when we do multiple trials, 5 is the bare minimum that I'd like to see. Occasionally we will do 3 in these labs, but 5 is the bare minimum I normally like. But if you talk to a statistician, they would say you shouldn't be messing with statistics until you get to, 50 or 100 trials. But we're going to go with it as is because that's the way we do. Okay. So now that you have that idea of what the instrumental uncertainty is, I'm going to tell you that there's also an uncertainty inherent in the actual object you're measuring. So, for instance, when I measured H and I got these 1, 2, 3, 4, 5, 6 different measurements, then I measured it. And then what I would do is like lay the meter stick on the device, I mean, on the object I'm measuring, and make sure it's really aligned, parallel properly, and all that good stuff. Make sure I've got the one end right at the 0 mark, or if the device is mauled, you maybe started at the 1 mark, and then you read the measurement. Then you take the device, the measuring device, off the object, put it back on, maybe at a slightly different place, and measure it again, and then again, and then again, and then again, and you'll have measurements that actually vary from one trial to the next normally. Okay. Now, your job is to take that mean to represent the value. In other words, take the average of all those measurements, and that's going to be your best estimate of the result. Again, with the caveat that a weighted average would have been better. And then you're got to figure out, well, now what is my uncertainty, and therefore what should I round this number to? Well, that's where the uncertainty calculations come in. It turns out that you want to have some idea of how far off your measurement is in a particular trial from what you think is the actual result. And that actual result is usually what you call the best estimate. Or, in other words, the average that you took, or under the caveat, the weighted average that you took. So you might think, hey, what if I take the weighted average or the average, whatever the best estimate is, what if I take that best estimate and subtract from it trial 1, and I'll call that the deviation of the first trial. And then I take that measurement, best estimate of the measurement minus the trial 2 value, and that's the deviation for the second trial. And you keep doing that for each of the trials, and you say, okay, now I'm going to average it. Okay. If you actually take the average of all of those individual values, what you'll discover is you get 0. Okay. So the average deviation is not a usable quantity. In fact, you can prove it's mathematically got to be 0. I did it yesterday with some real numbers and threw it in an Excel spreadsheet just to make sure everybody could see the action going on. And when I did the sum of the deviations instead of the sum of the squares of the deviations or anything like that, when I did the sum of the deviations, I got something something like 1.4 times 10 to the negative 16th. So that is zero in the computer world. So you can see it clearly is zero. So that's what you need to figure out is how do we get a good measure of how close our data is to the best estimate, because if it's all the trials are very, very close to the actual average or best estimate, then you have a high precision experiment. And that is more likely to be a high accuracy, even though accuracy means something different. But we need to figure out some way to get a scale on how bad or how good the precision of the experiment is. So if you notice, there's this thing called a bell curve, and that's sort of the picture we're working on, where the peak is actually the mean value. And if that bell curve is wide, that means there's a huge amount of uncertainty. If that bell curve is not wide, then that means it's a small amount of uncertainty, and therefore the precision is really good. Okay, so a tall, narrow Gaussian curve or bell curve would represent a very precisely done experiment, whereas a fat Gaussian or bell curve would indicate that it is a less precise experiment. Okay, so what is our thing that we're going to do? Well, now I'm going to go ahead and share my iPad screen with you. Oops, I thought it was. There it is. I'm going to share my iPad screen with you, and that way I can write some of the stuff that I'm telling you. So here it is. It should pop up any second now. There you go. Okay, so we're now in the iPad document, and now I can talk to you about what we were doing. So, for instance, we were talking about these measurements, and the measurements I had were 56.40, 56.38, and these are all, I'll call these H in centimeters. Notice if you write numbers without units, then you have to like put them in a column or put them in a row, and then have the unit at the left hand side of the row, or the units at the top of the column, so that we can know, oh, each of these numbers is measured in centimeters. So I've got another 56.38. I've got a 56.41, and I have a 56.40, and I have a 56.39. Okay, that's my three trials. Now, the way you go about calculating an average, as I told you, the formula would be this. So H average could be either called H with a bar over it or be put in brackets like that. Those are two common symbols or signs that we use for averaging. The mathematical formula for just a regular average would be basically the summation from I equals 1 to n, where n is the number of trials, of, in this case, h sub I, and then you're going to divide all that sum by the number n, which was the number of trials. So that is our average formula. So let me rewrite it because it was getting so close to that top part it didn't look too good. So it's the summation from I equals 1 to n of, there I go again, right next, of h sub I, and then you divide all that by n. The weighted average, by the way, just so you'll know, I set it all out in nice ways, and I picture numbers that way, but I know most people don't necessarily aren't able to see numbers that way and really work through them. So the weighted average, and there's other ways to do it, by the way. I'm going to just show you a couple. A weighted average would be uh, 1 over the error 1 squared. So this would be the error. That sigma symbol that I use would be the uncertainty that that lab has done historically. So it might be, like I said, the 0.0001 for the Nobel laureates. And you're going to multiply it by X1, which is the result that that lab got. then you're going to do the same thing with the second lab, which had an error or an average uncertainty of sigma 2. You can square that and say that multiplied by the result that lab 2 got. And you keep doing that plus dot 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 on up to 1 over sigma n for, well, let's do a different n here just because I don't want you to think the n here is the same as the number of trials. The n here is actually the number of labs that are doing the project. So I'm going to subscript it with, uh, let's say, n sub L for the number of labs. Now, as you know, the uncertainty has units of whatever the uncertainty of the, or whatever the units of X is. So for, in the case of H would have units of centimeters and the uncertainty would have units of centimeters. So if you take the units of centimeters and flip it over, that quantity has units of 1 over centimeters. But then if you square it, it has units of 1 over centimeters squared. So right now we're looking at a 1 over centimeter squared times a centimeter. So this result, at least in terms of the numerator, is just going to come out as 1 over centimeters, and that clearly can't be used. Okay, but the way we finish it out is we take and sum up all those weights, which would be 1 over sigma 1 squared, that's one weight, plus 1 over sigma 2 quantity squared, that's another weight, plus dot dot dot, plus 1 over sigma n lab squared, like that. That is your weighted average. You could also do it without squaring them. Then the formula would just be something along the lines of this. It would be 1 over sigma 1 times x1 plus 1 over sigma 2 times x2 plus dot 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 plus 1 over sigma n lab times x in lab, and then you divide all that by 1 over sigma 1 plus 1 over sigma 2 plus dot 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 plus 1 over sigma n sub L. Okay, so that's your two weighted average formulas that you could possibly use. You could imagine you could actually do it with a third power of the uncertainty or a fourth power of the uncertainty. It's more a matter of, do you really want to hyper focus on the thing that has the least average, the least error, and that's what the weighted average does. So if you really want to hyper focus, squaring the uncertainties in addition to flipping them over is a good way. But you could even amp that up more by cubing it, and amp it up more still by taking the fourth power. I generally just do the square on everything I do when I do a weighted average. Okay. So I was telling you one of the things we could do to estimate what the uncertainty is we could take the deviation and average that. Well, the average deviation would be this quantity. So this is average deviation. And deviation is a quantity that I've given this name to, but it really is just the mean minus a particular trial. You could even put it in the other order. You could say the particular trial minus the mean. It doesn't really matter, but one result's going to come out negative, the other result's going to come out positive, more than likely. So the average deviation would actually be, in the case of X, or excuse me, in the case of H above, we would say, okay, here's the best estimate of H. I'm going to subtract from that H1, and that's going to be my deviation. But then, actually, I need to lower this because it's going to run into what I'm doing here. Let's see, cut, and let's see, paste. So I'm going to bring it down a little bit further like this so I can have more room. Okay, so that's our first deviation. Then our second deviation is going to be the best estimate of H minus H2, the trial 2, and then plus dot 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 for each of the trials. In this case, I only went up to 6, so capital N is 6. So I'll say up to H average minus H6. And then, of course, since you had 6 measurements, you're going to divide that by 6. Well, when you actually do that math, watch what happens. We're going to get 6 times H bar, or H average. I'm sorry, I obsessing about individual symbols. I really shouldn't be. But you can see that I clearly get six of those average H's from this one, from these in here, and then from this one. Now, that's what we get, and we can see that that is in fact divided by 6 because that's part of the fraction. But we also have minus because each of the trials is led by, or each of the trial results is led by a negative. So I'll put a negative here. In this case, you're going to get H1 plus H2 plus dot 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 plus on up to H6. And then, of course, you're going to divide that by 6 because that's the denominator that we have. And what you see by doing this is the first number, 6 H average over 6 is just H average. And when you calculate H1 plus H2 plus H3 plus H4 plus H5 plus H6 divided by 6, that's just H average. And you see that, in fact, the result would be 0. That's why the average deviation is not helpful. What you should be realizing is the fact that you're just as likely to have measurements higher than the average as you are to having measurements lower than the average. And because of that, the average of these deviations tends to be 0 because it's just as many above as it is below, and you're always going to get 0. So what we might do to correct that is we might consider the deviation, but this time take the absolute value of it. That works. You can actually do that, but it's not helpful because the absolute value is a nasty function to work with. It's literally a piecewise function. So, computers don't do it very easily. Usually you have to have some human involved. It's just a pain. So what we do instead is we just take the deviation squared and we try to average that. Now, if you take the deviation squared, remember the units of the deviation are the same as the units of the measurement. So you'd end up having the deviation squared. If you summed all that up, it would come out in units of centimeters squared, in this case, a H. So that's not very helpful because I can't add something with units of centimeters squared to something with units of centimeters. They have to have the same units. So what you might think of doing is, okay, I'll take the average and then take the square root of it. And there you're starting to get to the idea of what the standard deviation is. But it turns out that the result that you're getting going for, which is some explanation in terms of like a Gaussian curve, where if you measure all the, or if you take all the area under the Gaussian curve between the mean minus one standard deviation and the mean plus one standard deviation, that should result in 68.1% of the data points falling in that area. If you go from the mean minus two standard deviations up to the mean plus two standard deviations, that should bring you up to about 95.4% of the data points. And if you go to three standard deviations, that would be the mean minus three standard deviations and the mean plus three standard deviations. The number of trials in between those two lines under that Gaussian curve would actually be 99.8%. That turns out to be a really useful paradigm. And what we discovered is if the number of trials that you have is a really big number, then the average works great. But if the number is not that big, if you only have like 5 or 3 or 6 trials or something like that, then we want to not divide by n. But what we've discovered is dividing by n minus 1 works best. So that's what we are actually going to define our standard deviation as. So, this one does not work. So we're going to do the standard deviation. And the standard deviation, I use the symbol S and then I subscript it with whatever variable we're talking about. So for instance, if I call the variable X as opposed to H, then the standard deviation would be S sub X. And the way you calculate it is this. You take the square root of the sum. So we're going to sum from I equals 1 to N, where N is the number of trials again. Gotta erase that. Up, stupid me. Okay, so where N is the number of trials, and that summation is the mean value of X minus x sub I, and then that quantity is squared. So that's what we're going to do for the top of the standard deviation. We're going to take the deviations and square each one and add them up. But then we're going to, by making an average, which is what we're shooting for, we would have just divided by n. But as I just told you, we're used to working with small numbers, so we can make that more apropos by dividing by n minus 1. So that's the convention that we've made. So this is the formula for the standard deviation, and your Excel program has it. And if you have a scientific calculator, it almost certainly has a statistics package that will automatically calculate this for you. Excel does it as well, and stuff like that. But that's what you're going to do with this lab is you're going to do these types of calculations by hand, and then you're going to use either your calculator, if you have a scientific calculator, with the statistics package, and you can look up or have the manual for it. If you can look up how to use the statistics package, I want you to do that. If you don't have that information about your particular scientific calculator, or you can't find that particular information on a Google search on the web, then you should go ahead and just use Excel, and that'll count for it as well. However, if you do this lab and you do the results with Excel and you do the results with your calculator and you submit both of them and tell me that you've done those, then I'll give you extra credit for doing more of the work, because it really is useful for you to know not only how your calculator statistic package works, but how Excel works to do it. And you're also getting the advantage of doing it by hand, which you'll see in a table in a second. So that's our standard deviation. And you might think, okay, well, now we have something we can put after the plus or minus. Well, sort of. We don't have that actually, because this is not what you're supposed to put out after the plus or minus in a number. So if I reported, for instance, H was 25.4 plus or minus 0.3, okay, that plus or minus zero point 0.3 is not the standard deviation. It's what we call the standard error, or a more useful and a more, I don't know, explanatory term would be that it is actually this standard deviation of the means. That's another phrase they use. So the standard deviation of the means is another phrase we use for the standard error. But let me explain what the standard error gets you, or the standard deviation gets you, and then let you see what the standard error gets you. The standard error, or the standard deviation, which is the S value that I just showed you. What that does is, if you consider a whole classroom, for instance, and they're each, let's say each lab station, and there might be hundreds of them, hopefully, each lab station is doing their own measurement to determine H or X or whatever. If you calculate that H value from each of those groups, then what you're going to get is a H value from one lab group, an H value from another lab group, a H value from another lab group, a H value from another lab group, and you're going to take the average of that, or like I said, the Holy Grail would be the weighted average, but we're not doing that. But that would be your best estimate. But if you then calculate the standard deviation, what the standard deviation does is it tells you what number of those individual trials, how big of a range of data is that within the 68.1%. So we're actually finding the probability, the 68.1% probability of finding the individual trial within one standard deviation. We don't want to know about individual trials, what they're going to result in. What we want to know is what independent labs would get. So instead of doing that, we do the same process that we came through in recognizing and creating the standard deviation. We do that same process again, but this time we do it acting on the means of all our individual labs, which is sort of the same thing as the means of each individual lab group. Okay, it's just I'm normally thinking that an individual lab group would just do one measurement and give you that. So I'm thinking of the trials. So the standard deviation allows you to figure out how many trials fall within one standard deviation, and it's supposed to be 68.1% of them. How many standard deviate or how many trials fall within two standard deviations, and that's supposed to be about 95.4%. And then how many fall within three standard deviations, that's supposed to be 99.8%. But that again is the number of trials. It's not the number of actual results. So doing this up a level again, in other words, instead of me taking an individual trial from each lab group, I'm now going to take the mean from each lab group. And if I take the mean of each lab group and then calculate the standard deviation of that, what I'm getting is the standard deviation of the means, which is called the standard error. And it sounds like a real nightmare to go through that calculation, but let me show you how simple it is. So here's the standard error. The standard error is often written as a sigma, just like the uncertainty is, because that's what we use the uncertainty for. So this is the quantity that's supposed to go after the plus or minus, and what it is turns out to be the summation from I equals 1 to n of x bar minus xi squared divided by n minus 1 and then divided again by n. So it's literally just one extra factor different from the standard deviation. And because of that, we can see that this is the standard deviation divided by the square root of the number of trials. So that's the result we want. So what we have to do to calculate what comes after the plus or minus after we do a series of measurements is we're supposed to calculate the standard error. We do that by first calculating the standard deviation and then taking that standard deviation and divide it by the square root of the number of trials. When we do that, that's when we get the number that comes after the plus or minus, with one caveat. Remember, I told you before you do any of this measurement, you have to estimate what the instrumental uncertainty is. So if you've done that, now then you now have an instrumental uncertainty written over here somewhere, and it might be 0.001, or it might be 0.01, or it might be 0.03, or whatever. The main thing is you now have that instrumental uncertainty, and you have the standard error, and you have to take the largest of the two. So a lot of times you end up doing this tedious calculation of standard error, first standard deviation, and then standard error. And it turns out that you can't use that result because that result turned out to be smaller than the instrumental uncertainty. And you can't use statistics to get rid of instrumental uncertainty. So in that case, you have to put it after the plus or minus. So I'm going to write a little rule down here, or a little explanatory note here. It says, this is what goes after the plus or minus in a result unless sigma instrument is greater than sigma. If it's greater than sigma, then you have to use the uncertainty. Okay. So the standard error is what goes after the plus or minus if and only if that is the same size or bigger than the actual instrumental uncertainty. If it's the instrumental uncertainty that's biggest, you're just going to put that there. And additionally, if you find that the standard error is 0.001 or 0.004 or 0.003 or whatever, there's no chance in heck that you're going to know what that third decimal place is, much less the fourth. So what our rule is in determining what we round our average to, our best estimate to, is whatever the last digit of the standard error or the instrumental error, whichever one you have to use, whatever place that last digit is in, that's the place where the first sig fig of the instrumental uncertainty or the standard error is. So what do I mean by that? Well, what that means is, for instance, in this example that we're looking at right here, we calculated that H bar, actually, I should go back to blue now. We calculated that H bar, which is also equal to H average, in this case is 56.3 or 93333 centimeters. It actually goes on beyond that, but I just wanted to make sure I put more than enough digits. So that's what the calculation of the average of those six values came out to be. When I took the deviation and squared it, and then take the other deviation and square it, and the other deviation and square it, other deviation and square it, and other deviation and square it. Once I've taken all the deviations squared, I add those quantities up. That gives me the numerator under the square root in both the standard deviation formula and the standard error formula. And then I have to divide that sum by n minus 1 and then take the square root of that. That would give me the standard deviation. When I did that calculation, I got the standard deviation of h is equal to 0.02, or excuse me, 0.121 centimeters. Remember, the standard deviation will have the same units as the quantity that you're calculating the standard deviation of. So that's what happens there. Now, if we want to calculate the standard error, then what we do is we say sigma sub x is equal to the standard error, or excuse me, standard deviation divided by the square root of n. So we'd take 0.0121 centimeters and we're going to divide that by the square root of 6. So when I do that math, let me get my calculator out. When I do 0.0121 divided by, I will use parentheses here, square root of 6, and I get 0.02. Oops, never mind. I see that my calculator, my fat fingers hit the multiplication button instead of the division button. So 0.0121 divided by, and that gives me 0. Oops, 0.04939 centimeters. So that's the standard error, but we might have found, for instance, the instrumental error. We might have found that the instrumental error was plus, or was actually, let's just write it with, oops, I don't know what I just did there. Okay. Uh, what we might have found that it was 0.02 centimeters, because a meter stick is normally not better than plus or minus zero point zero 0.01. It's normally even zero point zero 0.02. So since sigma instrument is greater than sigma x, we must use sigma instrument as sigma x. And that means in this case, we'll report h is 56.39 plus or minus 0.02 centimeters. So the important point to notice here is the error has been rounded to 1 sig fig. So 0.02 is the error, and that sig fig is in the hundredths place, and that has to line up exactly with the digit that you round the actual best estimate to. Now, some people will say if you get a standard R, a standard error, R instrumental error, If you get one that's like 0.01457, something like that, centimeters, if you get that, then it's clear that you don't know the second decimal place because that value of 1 is in the second decimal place, and you certainly don't know the second value. But the problem is when that leading digit is 1, if you round that to just one sig fig, then you're losing 40% of the information because the next digit is 4, maybe even 5 if you round it. So you're missing 40 to 50% of the information by rounding it to one sig fig. So when people get a 1 as the first digit of their standard error or their standard deviation, or excuse me, their standard error or their instrumental uncertainty, they often will take the time to go ahead and add the second digit if it's like a 3 or a 4 or something like that. If it's a 5, they go ahead and round it up to 2. Okay. I'm not going to take off for you doing that. I'm not going to take off for you not doing that either. So you don't have to worry about that rule. I just want you to understand that sometimes someone might write, if the experiment had been different, you might have found that X is equal to, let's say, 32.987 plus or minus zero point 0.0, let's say 1.4 centimeters. So in this case, what you see is the decimal place of the last digit of the error is exactly lined up with the last digit of the best estimate. Okay, that's again where you're supposed to round it. But most of us normally just use one sig fig as the error, and that's fine. I just wanted to let you know that sometimes people will use two digits when that standard error or that instrumental error is a 1. The next digit will be included just because it's such a large fraction and 1's so small. So that's the process you go through for figuring out what a best estimate of H is, as well as what error I should assume it has. So that's the sort of rule, if you will. You're going to calculate the standard deviation, then you're going to divide the standard deviation by the square root of the number of trials. That'll give you the standard error, and then the standard error is supposed to be after the plus or minus, unless that standard error is smaller than the instrumental error. So now we are actually at the 9:06 point, and I really had only planned on you guys me doing an hour of information. So if y'all have to go somewhere, you're completely free to go. I'm just going to keep on talking, but you can also ask me questions. You haven't really asked any yet, but you're welcome to ask me questions as I go. But you're also welcome to split if you have something to do. I'm just going to continue as if you are here. So we've now sifted out exactly what we should use as our error, and it's supposed to be the larger of the two. It's the standard error and the instrumental error. However, once you start to use those uncertainty measurements, those measurements that have uncertainty in them, like for instance, maybe we're calculating the volume of a rectangular solid, and this h is just the height of that rectangular solid, then what you're going to do is take, three measurements. You're going to take h, w, and l, which are the dimensions of a rectangular solid, and you're going to multiply h, the best estimate of h, times the best estimate of l, times the best estimate of w, or W, I think is what I called it for width. And that'll give you an area. But there's no way to have an instrumental uncertainty on that because you didn't use a device that directly measured the area. You used a device that measured height, length, and width. So in this case, you don't have something like instrumental error to compare to. You just have to figure out what the error in the answer is. And that's what propagation of error is about. So in some sense, you got to realize that what we're going to do is by creating a quantity that requires us to calculate using measured quantities, we're creating a function. Specifically, in this case, the function would be the V, the volume, as a function of W, L, and H. And the function is equal to W times L times H. Okay, so that's a multivariable function, and you haven't really learned how to deal with that in calculus. You don't really learn how to deal with that until Calc 3, but we have a way of doing it. So I'm going to start off with telling you how you deal with uncertainty just as a single variable function instead of a multivariable function, and then I'll generalize that to a multivariable function. So, in order for me to explain that, what we're going to do is we're going to imagine that this is f equals y, say, and this is x, and let's say this function right here is f of x. If this is the x value that you have, let's say call it x bar because that's our best estimate. Or actually, let me go ahead, since I keep calling it x bar, let me use the bar because that's a lot less writing. So if you take this particular x value and you put it in the function, then the function, by definition of what the function is going to give you this value, which is f of x bar. And that's really like the volume formula. That would be volume is equal to the volume as a function of w bar, l bar, h bar equals w bar times l bar times h bar. That's really what the volume function is. So let me just write that so y'all have an idea what I'm talking about. Volume of W, L, and H is equal to W bar times L bar times H bar. Okay, that's a multivariable function, but we're talking about a single variable function right now. So if your uncertainty is sigma, it could be, we would call it sigma x, but that could be a result of instrumental uncertainty in x, or it could be the actual standard error in x. So I'm just going to use the symbol sigma. So what we know is our x value is supposed to be x bar plus or minus sigma x, where this is sigma instrumental r sigma x, which equals sx over the square root of n. So that's the way you're supposed to record the data. So what we need to figure out is, what if my value is not x bar, but x bar plus sigma x? Well, in that case, the function is going to be read as this, and in this case, it's f of x bar plus sigma x. And that's the actual value when we evaluate the function at x bar plus one standard error. So I think you can recognize that this distance here, I'll zoom into it and say this distance right here is sigma f. Okay, so that little distance right there is representative of the state of the error in the function. So in other words, we're taking the error in x and adding that error in x to x, and then we're seeing what becomes of f now that it's f not of x, but f of x bar plus sigma x. And it's that small little difference right there that we should put after the plus or minus in the calculation. Now, I suspect you all know that, in fact, that sigma f is just equal to the derivative of f with respect to x, and we always want it to be positive, so we're going to put absolute value bars around it, and then we're going to multiply that by sigma x, because all of this has to be factual because of this little triangle. The little triangle we have is the curve going through here like that, and then we have this other spot like that, and we have a line like this. This value down here is x bar. Uh, I made that a little too far. Let's see. So that value is x bar. Dang it, I don't know why this thing's not letting me write there, but it's being a pain. So let me get rid of that and do it a little farther from the edge. But the triangle I'm trying to show here is the dots from the function. That was supposed to be black. The dots from the function go like this. This is the value down to x, and this is the value down to x plus delta x. So straight below here is x bar, and straight below here is x bar plus sigma x. Then you also have the tangent line, or the secant line is technically what that's called, until you take the limit as delta x approaches zero. But what you see right here is this quantity is sigma x, and what you see right here is this quantity is sigma f. And now I think you can see why this formula is the result that we need for our one variable function. Okay, so that's a propagation of error formula. That tells you, hey, if you're doing a mathematical operation f of x on x, then the error in f is going to be the error in x multiplied by the absolute value of the derivative of the function of x. Okay, and if that function of x still has an x in it, that means you have to put the x in terms of the best estimate of x. So that's true as well for all these formulas. When we actually have to put in an x or a y or a z or a w or an l or an h, we're expected to put in the x, the y, the z average. In other words, the x bar, the y bar, the z bar, the w bar, the l bar, the h bar. Okay, but now I need to generalize this to multiple dimensions, and before I do that, I want to show you just one example. Let's say, let's assume f of h converts h from units of centimeters to units of meters, then f of h is equal to 1.00 meters divided by 100.00 centimeters times h bar. That's really what the function's supposed to be. And I put the bar up there for you to realize that the h that you're supposed to put in there is the best estimate, but it makes it a little confusing. So I'm going to erase it now, but I just put it up there for that split second to remind you that that's the value you're going to use. Now that we have that, we can say that the derivative of f with respect to h in this case, actually, derivative of f with respect to h is in fact 1.00 meters divided by 100.00 centimeters. So that means, of course, the absolute value of the function is also still that same quantity. And now we can see that sigma f is equal to the absolute value of df over dh times sigma h. So this means I'm going to take 1.00 meters divided by 100.00 centimeters in the absolute value bars, and I'm going to multiply that by the uncertainty in h, which is 0.02 centimeters. So when I do that, you can see that basically what I'm going to get is 0.0002, and now that unit canceling out here, this centimeter down here canceling out with that centimeter up there, leaves the unit in meters. And I think you can see that that is exactly the same. That 0.0002 is exactly the same in meters as 0.02 is in centimeters. So hopefully that's pretty conclusive evidence that convinces you that in fact this is the appropriate way to propagate error, at least with a one variable function. Any of you have any questions on that? All right. Sorry if y'all heard all that. I've been taking a sip of my coffee. Imagine it's not a very Pleasant sound. All right. So now that we have that, I'm going to show you. I'm not going to derive it, but I think you'll see that it's reasonable, at least from looking at the generalized one and contracting it down to the single variable function. You'll see that that's obvious. So hopefully that's enough for you. It's a little bit involved. I can do the derivation. I've done the derivation in my YouTube videos, so you can find one there, but I'm just not doing it now. So generalization of propagation of error formula. So the generalization is sigma of f, if you're assuming f is a function of x, y, and z, for instance, is equal to the square root of, and here's the part where I'm introducing some math that you haven't been taught more than likely, the partial derivative of f with respect to x quantity squared. Notice I'm writing what looks like backwards sixes. That's the symbol we use for partial differentiation instead of regular differentiation. And I have to also multiply that by the square of the uncertainty in x. And this is a function of three variables, but you can extend it to any number of variables just by adding more terms. But I'm pretending right now it's three variables, x, y, and z. So the next part is the partial derivative of f with respect to y times sigma y squared plus the partial derivative of f with respect to z, quantity squared, sigma z squared. So if you try to imagine this as only being a function of x, then the sigma y and the partial derivative of f with respect to y is going to be zero, and or actually more specifically, just the partial derivative of f with respect to y is going to be zero, and the partial derivative with respect to with respect to z is also going to be zero. So if you imagine eliminating these terms, you would just have the square root of a square. And that, by default, since it's a positive square root, has to come out to the absolute value of the derivative with respect to x. But since now the function only has one variable, I don't have to write the backwards six. We have to write the regular d. So you see that this does, in fact, it reduces to sigma f is equal to the absolute value df dx times sigma x. So I think you can see it easier that the special case is the one variable function relative to the general case, which is the big formula I just gave you. So this is our actual propagation of error formula. But before I can even make sense of that, I got to show you a little bit about what a partial derivative is. Again, I'm taking way longer than I normally do, but I really don't think it's fair to give you all this document without explaining this stuff, even though it's all written in the document and you can get it. So I just want y'all to have a record of it. So, what is the partial derivative of f? Well, I will tell you that df, let's actually go back to a different color. Let's go to blue or purple. So, df over dx, you probably remember from your calculus days and your pre-calculus days, was f of x plus delta x minus f of x divided by x plus delta x, which is your final x, minus x, which is your initial x. But, oops, I forgot to leave space for the limit. So that is supposed to follow the limit as delta x approaches zero. That's what the derivative of f of x is. You evaluate the function at f of x plus delta x, which is just like what we did in this graph right here, and you subtract from that the f of x, which is exactly what we're getting in this little part right here. That thing is the f of x plus delta x minus f of x. That's exactly what that distance is, and that's exactly what delta f is. So that's what's going on here. Now, to show you the definition of a partial derivative, and I'm again going on the assumption that the uh, function is a function of x, y, and z, this is going to be a limit as delta x approaches zero of, here's the different part, it's x plus delta x, y, z, minus f of x, y, z, divided by x plus delta x minus x. So that is the definition of a partial derivative, and you can see that they're pretty much just pretending like the y and the z and any other variables in the function, we're pretending like those are just constants. That's the way you do a partial derivative. You pretend the other variables are a constant, and the one that you don't treat as a constant is the one that's under the that's in the bottom of the symbol for the partial derivative. So let me show you a couple of examples just to make sure you guys know what a partial derivative is and how to calculate it. So if we say f of xy is equal to x plus y, then we can say the partial derivative of f with respect to x is equal to the derivative. Watch what I'm doing here. I'm playing a trick. I'm pretending like y is a constant. So I'm going to say the partial derivative of f with respect to x is really just the derivative of f with respect to x, except I've replaced y with 4. Okay? So I'm just physically pretending y is a constant. Okay. Now, if you take the derivative of this, you can see this is a one variable function. So we know how to do that. The derivative of x plus 4 with respect to x is just 1 because it's literally the coefficient of the 1. Now, since the y did not appear in the final answer, we don't have to go back and put the y in, but that's normally what we would do when we're using this trick to trick ourselves into doing a partial derivative. So that's the partial derivative. Additionally, the partial derivative of f with respect to y is the same thing as d by dy of 3 plus y. So notice this time I'm pretending that x, or excuse me, that, yeah, it is supposed to be x, but this y did not look very y-like, so I'm going to make sure y'all know it's a y. So what we're doing is pretending the other variable, which was an x, is a number, and I specifically chose to pretend it was the number 3. So when I take the derivative of 3 plus y, I still get 1 as well. Okay, so that's the way you take a partial derivative. Now that tells us, in fact, since we have those derivatives, that the uncertainty in f, where f of x, y is equal to x plus y, this is equal to, according to our formula up there, 1 squared times sigma x squared plus 1 squared times sigma y squared, which equals just sigma x squared plus sigma y squared. So that is the formula for the propagation of error when you add two numbers. If you add x plus y or if you add y plus x, you're still going to get the same result. Now let me try f of xy is equal to x minus y. In this case, we're going to say the partial of f with respect to x is equal to d by dx of x minus 4, which again is just 1. Similarly, the partial of f with respect to y is d by dy of, in this case, it's going to be 3 minus y, which in this case gives me negative 1. So that's how we did the partial derivative in that case. Notice the y didn't exist after the derivative, or excuse me, the x didn't exist after the derivative, so I don't have to go back and replace the 3 with an x, but that's what you normally have to do. And the same thing with the df over dx. Since the y disappeared, we don't have to put a replace the 4 in there for the y because the 4 never showed up. So now we can say the uncertainty in f is equal to the derivative of f with respect to x is 1, so we're going to square that and say sigma x squared, plus the derivative with respect to y is negative 1, so we're going to square that and multiply it by sigma y squared, and lo and behold, you get exactly the same formula that you got when you added the two. Okay, so let me show you another one. I'm teaching you not only propagation of error right now, I'm also teaching you how to take partial derivatives. So we can now say if f of x, y is equal to x times y, then the partial derivative with respect to x is equal to d by dx of, now this time we're taking a partial with respect to x, so that means we're supposed to pretend that the y is a constant. So I'm going to say 4 times x is what that is, because the order of multiplication doesn't matter. X times y, y times x, the same thing. So I just made it y times x to make it look more natural, and I replaced the y with a 4. Now, when you take the derivative of 4x with respect to x, you get 4. But it's not really 4. 4 is what we use to substitute for y. So the answer is technically y. So that's the derivative, the partial derivative of f with respect to x is in fact y. The partial derivative of f with respect to y is d by dy of, now this time I'm going to take the x and replace it with a 3, so I get 3 times y. Now the derivative of this with respect to y is of course just 3, but 3 is what we use to substitute for x, so I have to go back and put it as x, and that's what it is. I don't expect you guys to go through this step when you're doing it. You should just be able to take the derivative without going through that step, but if you need to for a couple weeks, go for it. That's fine, okay? Now that I have that, I can say that the uncertainty in the function, in other words, if I take an x that has an uncertainty and I take a y that has an uncertainty and I multiply x times y, the result, the best estimate of f of x, y, is x bar times y bar. And the uncertainty in that is sigma f, and that's given by the partial of f with respect to x squared, so that's going to be y squared, excuse me. I forgot I changed it to y. So that's going to be y squared sigma x squared plus x squared, oops, plus x squared sigma y squared. And that is the actual formula, but it's not a very helpful one. I mean, you can use it and it's fine, but I'm going to show you something that will make it a little uh, easier to remember and a little more universal. Okay, you'll understand what I mean by universal in a second, but that's the formula. So it turns out that when you're multiplying variables like x times y times z or x times y over z, multiplying or dividing, in other words, or x times z over y or z times y over x, any of those combinations, when you're dealing with stuff that's purely multiplication, it's almost always better to calculate not the standard error, but or not the error like I showed you here, but what we call the fractional error. So I'm going to calculate that fractional error with this problem so you can see how much nicer it is. So the fractional error, also called there's another phrase for it, the fractional uncertainty or something like that. But the fractional error is called by the symbol sigma f over f, and that symbol is actually the formula. You take the error, the propagated error of f, and you divide it by the function f. And again, like I said, whenever you see an x or a y in a formula, like you see that y there and that x there, what if you want to use that formula, you're supposed to use x bar and y bar. So you're supposed to use x bar for the x and you're supposed to be using y bar for the y to put that in that formula. So just keep that in mind whenever you do this error propagation stuff and you get an x or a y or a z or a w or a q, you're supposed to put in the best estimate of the x, the y, the z, the w, or the q. So in this case, what we're going to do is take the formula that we already computed for the uncertainty, the sigma f, and I'm going to make a taller square root so I can fit everything under it. But basically, I'm going to take the numerator, which was y, oops, left off a square there, y squared sigma x squared plus x squared sigma y squared. That's the uncertainty in f. Now I'm also planning to divide by the function f, which is x times y, but I want it under the square root. So the way we can force something that's in front of the square root to go inside of the square root is we have to square it to put it inside because that's the opposite operation from taking the square root. So I'm going to square the function, which is x times y. That gives me x squared times y squared. Now, if you look at this as two separate fractions instead of one big fraction, what you'll see is that when I look at this fraction, this y squared is going to cancel out with that y squared and just leave an x squared in the bottom. And when I look at this fraction, this x squared is going to cancel out with this x squared, and that's just going to leave a y squared in the bottom. So we get a really nice result in terms of the fractional errors of the variables. Specifically, we get sigma x over x squared plus sigma y over y squared, like that. And that's again just remembering that the formula is the symbol. So when we broke apart those separate fractions, we were left with sigma x squared over x squared. So that is the formula for the square of the fractional uncertainty. So I just put the parentheses outside and put the exponent of 2 on it. Now, that is telling us that the fractional uncertainty of the function f is equal to the sum of the squares of the fractional uncertainties of the variables. So that's a really, really big result. And let me show you why it's big. If we do the exact same calculation for a slightly different function, let's say f of x, y is equal to x over y, then the partial of f with respect to x is, I'm not going to use the training wheel method here. I'm just going to remind you that x times y, or x over y, excuse me, is the same thing as 1 over y times x. So hopefully that's enough for you to see, oh, the derivative of this with respect to x is just 1 over y. The partial derivative of this with respect to y is equal to, now in this case we want to think of it as x. I was supposed to be writing this in red. I'm going to erase it in a second anyways, but I want you to understand what I'm talking about here. X over y can also be thought of as x times y to the negative 1 power. So that you see it does sort of look like 3 times y to the negative 1 if you wanted to do it with the training wheels way like I was telling you a second ago. I'm not going to need to do that because I can do this derivative. The derivative of y to the negative 1 is negative y to the negative 2. So this is going to become, in fact, negative x over y squared. So that's the partial derivative of f with respect to y. It's negative x over y squared. Now I can compute that the fractional uncertainty, actually I'll start off with the regular uncertainty and then I'll calculate the fractional uncertainty. The regular uncertainty is the square root of 1 over y squared sigma x squared plus negative x over y squared squared sigma y squared. I can make this a little neater by saying the square root of 1 over y squared sigma x squared plus x squared over y to the fourth sigma y squared. So that is what the uh, propagated error formula is for x over y. But as I told you, whenever you're doing nothing but multiplications and divisions, it's probably better to use the fractional uncertainty and our fractional error. So that's what I'm going to do now. The fractional uncertainty, remember the symbol is the formula. So I'm going to take the uh, propagated uncertainty, the propagated error, and divide it by the function itself. That's 1 over y squared sigma x squared plus x squared over y to the fourth sigma y squared. But now I'm going to divide it by the square of the function under the square root, because to get it under the square root, we got to square it. So this is going to be under or over x squared over y squared. So now, just like before, when you try to break this up into separate fractions, you can see the 1 over y squared is canceling out with the y squared, and the x squared is going to be under the sigma x. So we're getting again the formula for the fractional uncertainty in x. And if you look at this fractional part, you see that the x squared in the top is going to cancel out with the x squared in the bottom, and the y to the fourth is going to cancel out the y squared in the bottom and just leave y to the second, which gives us sigma y over y squared, and that's the fractional uncertainty. So now what I have is, in fact, the square root of sigma x over x squared plus sigma y over y squared, like that. So we see that the formula for x times y is exactly the same as the formula for x over y. And I'll tell you, if you added another term, which is the fractional error of z over z, or the fractional error of z squared inside of that square root, then you could handle x times z, x times y over z, x times z over y times z over x. All of those all would have the same formula, sigma x over x squared plus sigma y over y squared plus sigma z over z squared, square root of all that quantity. Okay, so that's our propagation of error formulas, and that's partial derivatives. That's all the stuff that I really needed to teach you guys. Now, what I'm going to show you is, now that I've explained all that, hopefully you now understand the formulas and remember the rule. Any x, y, z, w, l, dot, 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 that appears in sigma f r, oops, r in sigma f over f is to be interpreted interpreted as x bar, y bar, z bar, w bar, l bar, dot, dot, dot. In other words, these lone x's or y's or z's that you see in one of the propagation of error formula, you have to take the best estimate of that. So there's a rule. The other big rule that we learned was that when we calculate our uncertainty, in other words, our error, our standard error, or our instrumental error, when we calculate that, we generally round it to one sig fig, and then that one sig fig is in the place where we round the best estimate to, so that they exactly are in the same spot. They line up. I did tell you you could, if that instrumental uncertainty is one, you can use it. You can write it as two sig figs, 1 3 or 1 4 or something like that. But I'm not requiring it, and I'm not going to take off for you if you do it. Okay. So that's the other rule is always round your result to the same place as the last digit of the instrumental uncertainty or the propagated uncertainty or the instrumental error or the standard errors. That was the word I was going for. All right. So now I'm going to stop sharing this iPad screen and go back to the document. So let me share my document with you, window with you real quick so I can finish off this introduction to the lab that went really longer than you guys really wanted, I know. But this is complicated stuff, and though I walk you through it in writing, I know it's hard to read stuff like that sometimes. I darn it and went to the wrong one again. Stop share, stupid head. It actually was my fault. I just was talking, and when I talk at the same time, it's not a good quality for a teacher. But when you're talking while you're doing stuff, you often make mistakes. So here's where we're at. Basically, what I did is I started off with this page showing you the 56.39333. I even showed you this standard deviation, and then I even calculated the standard error. By taking that standard deviation and dividing it by the square root of 6. But as you can see, that standard error turned out to be, uh, I think I did it in this one. Yeah, 0.00494. So that's where I calculated. That's what the values I was using was. I wasn't calculating them in real time. So this tells all those rules. The most important thing is to remember to record your hypothesized instrumental slash measurement error prior to performing the statistical analysis. Record even if there is no place to record it in your lab or any provided data tables. By the way, it is also proper to only record data using ink that cannot be erased. If you accidentally make a mistake in a measurement or in a recording the measurement, you should draw a thin, crisp line through the erroneous data in a way that does not prevent the erroneous number from being easily read. It is also advised that you note why the data was erroneous. Rule one was when several measurements are made of a single quantity, the average or weighted average is the best estimate of the value. Rule two, the larger of the instrumental slash measurement error or the standard error are to be used as the uncertainty of the measurement. Rule three, the uncertainty of a given measurement should almost always be recorded with one sig fig because if you don't know the leftmost leading digit with high certainty, we definitely don't know what the digits to its right are. The only time you may wish to use two sig figs is when the leading digit is 1 and the second digit is like 4 or 5 or something like that. In our labs, I will never take off for using this practice nor for not using it. Rule four, your measurement's best estimate should be rounded off at the same digit as the last digit of your uncertainty. And rule five, when using uncertain measurements to compute something else, you must use the best estimate for the values and the measure of the measurements and error propagation formula should be used to determine the uncertainty of the calculated quantity to learn where to round off the calculated quantity. So there's me telling you a standard deviation. This is the data table. So when you make a table like this, and you do have to make one for this lab, you have to at least fill one out that you'll see later. But what you do is you take the individual data points. This would be H1, H2, H3, H4, H5, H6, and we're going to put them in the data table. And then, like Excel naturally does, it's easy to just add these quantities up and put the result right here. And then the average is found by dividing that result by 6, and that gives me the 56.3933 that you see here. The deviation, in this case, I chose to use it as h minus h bar instead of the h bar minus h that I had been doing before. It doesn't really matter. Like I told you, you're going to end up squaring it when you really use it. But when I do that, I get these numbers. Summing them up is not important. We know for a fact that the sum of that should come out to be essentially 0. And here's the formula for the standard deviation, and here's the formula for the standard error. So now what we're going to do is take each of these deviations and square them. That's going to also, of course, get rid of the negative. So this is the deviation squared for the first trial, for the second trial, third trial, fourth trial, fifth trial, sixth trial. And just like the formula says, we are supposed to add up the squares of those deviations. This 0.0007333 is exactly what we get when we did that sum. Now, if we take that sum and divide it by 5 6 minus 1 is 5, and then take the square root, we get 0.012110601. Now, if we take that number and divide by the square root of 6, we get 0.0049444132. This is your standard error. This is your standard deviation. And what I told you is if your standard error is a 5 in the third decimal place, you definitely have no clue what the number is in the fifth decimal place. That's why we round the best estimate to the third decimal place in this case. Now, also in this case, if we found our instrumental uncertainty was bigger than this 0.004, which we did, then we're going to have to use the instrumental uncertainty instead of the 0.004. All right, so there's all those formulas. There's the propagation of error formula. There's the example I chose to show you just now, and these other examples I chose to show you. This is me showing you how to calculate those values, so on and so forth. This is me making derivations for the propagation of error for the volume formula, and these are the assignments, the questions that you have to answer. So I want you to show, in other words, do that same set of steps that I've already done for you. I want you to follow my steps really well and then not look at the video and do it on your own for x plus y. Then I want you to, watch the video, close the video, and then try to do it on your own for x minus y, and then try it again without the video for y minus x, and then try it for x times y times z, and then try it for x over y, and you should get all these. Notice I didn't do x times y times z, I just did x times y. So all it really entails in doing this from what I did for you was adding this extra term, or resulting in the addition of this extra term. But this one I did do for you. This one is the same one, but upside down. So that's again more practice, and this is a more complicated version. All of this I've given you enough to figure out how to do. This is the table where you're actually going to put in your numbers. Again, if you type the numbers in, that's great. That's why I gave it to you in Word format, but you need to make sure the colors of these numbers that you type in here are some color other than black, and you're going to do it here as well, and here and here. And again, if you're typing them in, those numbers have to be in a font other than black. If you're handwriting them in, it's fine, but even then I would prefer it to be a slightly different color than black, but you don't have to. I ask you, do your calculations match the results I gave in the introduction to this lab? And then number 9, learn to use your calculator statistic package or Excels if your calculator does not have such options by putting this data in and letting them calculate the mean. Does your calculator or Excel have a standard error function? Uh, in other words, you're looking to see when you plug these numbers into your calculator or into your Excel, does some number spit out that is the equivalent of our standard deviation, the 0.0049. If you find that, then yeah, I want you to tell me yes, it is, and tell me what symbol they're using. And then finally, I think this is the last one. Use the following data for the dimensions of a rectangular solid: 4.29 plus or minus zero point zero 0.03 centimeters, y equals 2.86 plus or minus 0.02 centimeters, and z equals 1.98 plus or minus 0.01 centimeters to calculate the best estimate for the volume of the solid. And finally, properly report the experimental value of the volume and its error uncertainty. So this is probably the most important words I'm going to say to you, because normally I'd take the time to show you another example, but I've taken almost 2 hours now, so I think I'm just going to explain it to you in words. To find the best estimate of the volume, we know the formula is x times y times z in this case. So I'm going to take the 4.29, which is the best estimate of x, and I'm going to multiply that by 2.86, and I'm going to multiply that by 1.98, and that's going to give me my best estimate of the volume, but it'll probably have way too many digits. So you just record that volume with, a copious amount of extra digits. Just make sure you got a ton of extra digits on there and write it off to the side somewhere. Then you're going to use your propagation of error formula, which, by the way, you've already done if you worked out This part right here, x times y times z, is the same thing as our volume formula if I call the length, width, and height x times y times z instead of w, l, and h. So this is the formula you're going to use. You're going to take the fractional uncertainty in x and square it, take the fractional uncertainty in y and square it, take the fractional uncertainty in z and square it, and then add those quantities and take the square root of that sum. So when you go to calculate sigma x over x, you're going to take the 0.03 and divide it by 4.29. That's the sigma x over x, and then you're going to square it. The sigma y over y is going to be the 0.02 over 2.86, and you're going to do that division and then square it, and then you're going to take the 0.01 and divide it by 1.98, and then you're going to square that. That'll be your sigma z over z squared. Then you'll add those three fractional errors and take the square root, and that'll give you the fractional error of the volume. But that's not good enough because the fractional error is going to have no units. You can't put something with no units after the plus or minus with something with units. So you've got to now take that fractional error and calculate the error from it. And you do that just by multiplying. Remember, the symbol is sigma v over v, which looks like if I just multiplied by v, I would have the sigma v. That's exactly why the symbol is the formula. So all you have to do is take the fractional uncertainty that you just calculated and multiply it by that volume with all those digits, and then that will give you the fractional uncertainty, or excuse me, that'll give you the uncertainty in the volume. You round that to one sig fig unless it happens to be one and you want to do that two-digit thing. You round that to one sig fig, and then you round the best estimate with all those digits to that same number place. You can keep extra digits, but you need to underline them. That way I'll know that, hey, these are not supposed to be sig figs. So that's it. That's what you got to do for this lab. I know that was a lot longer than you guys necessarily expected, but I do appreciate you coming. This will be posted online sometime today, but you're done. If you have any questions, stick around, ask me questions. I'll wait for the last person to leave before I close down the meeting, but you're free to go. Thank you very much. Oh, by the way, never mind, missed it. Did you have any questions, Darren? I'm looking in the chat right now. There it is. Thank you. Gotcha. Thank you, bud. Appreciate it, Derek. You have a good one, everybody. And I'm going to say bye bye.